Good morning, kids. Today we're going to talk about separation of variables to find the solution of a differential equation. This is really quite straightforward. I'll go through the steps and then I recommend you pause the video to take them down, and then we'll go through 4 different examples. If you don't have time to finish the video during class, it's part of your assignment. Just go home and finish watching it at home, and then do the assignment at the end of the video. But this is very straightforward, so I think you'll understand it quite easily. First step is to get all the x's and dx on one side and all the y's and dy on the other side of the equation. Make sure dx and dy are in the numerator if it's a fraction, okay? So you can't integrate if you have something over dx. It's got to be something times dx. Second thing is integrate both sides. Don't forget the plus c. You only have to put plus c on one side because if you move the constant to the other side, you still get a constant. Next, plug in the initial conditions if given to find the constant, and then you plug the constant back into the solution from step 2. And once you've plugged the constant back into the solution, you have a solution of the form independent variable equals dependent variable times something plus something, or whatever, some sort of an equation. Alright, so example 1, go ahead and pause the video and take those down. And then we'll do example 1. So here's example 1. Solve dl dp equals L over 2, L of 0 equals 100. So what we want to do is we want to divide both sides by divide both sides by L and multiply both sides by dp. Basically what's going to happen when we do that is those two things are going to switch, and that won't change the value of the proportion if those switch. So I get 2 times dl is equal to dp. I also multiplied both sides by 2 there. Okay, so once you get 2 dl 2 dl over L is equal to dp. Okay, so once you have that, you have all your L's on one side, all your P's on the other side, and you can integrate both sides. So when we integrate both sides here, what we get is the following. 2 natural log absolute value of L equals P plus some constant C. Okay, so now we're going to divide. We have to isolate the natural log in order to be able to solve this, so we'll divide everything by 2 here. Now, the 2 disappears here when we divide by it. We get a 1, so we get natural log absolute value of L equals P over 2 plus C over 2. But instead of saying C over 2, it's just another constant. Now, you can't say plus C again. It's a different constant, so call it plus D. Every time you do something to the constant, you have to change the constant. So now we have that, and the next thing we need to do is raise both sides to, raise e to the power of both sides to get rid of the natural log. So here, the e to the ln are inverses, so you end up with L over here equals e to the 1/2 P plus D. Now what that really is, if you think about it, is since when you multiply you add exponents, that would mean L equals e to the 1/2 P times e to the D. But e to the D is just a constant to a constant. So again, that gives you a constant. So what we do is we take this e to the d, and there will come a time when I'll actually skip this step, and we change it to another constant. Usually the last constant we use is a. Alright, so we say L equals a e to the 1/2 P. Okay, so our constant is in a different place than where we're used to seeing it. Now we we have it solved for L, and we're going to plug in L of 0 equals 100. All right, so at this point, plug L of 0 equals 100 so that we can solve for the constant A. So if L of 0 equals 100, that means we get 100 equals A e to the 1/2 times 0. Well, e to the 1/2 times 0 is e to the 0. E to the 0 is 1, right? So basically what we end up with is, oops, 2 pages later, hold on. What we end up with is 100 equals A. Now once we have 100 equal to A, all we have to do is take this and combine them together to get our final answer, which is L equals 100 e to the 1/2 p. So that is the particular solution of the differential equation, all right, where the initial condition is L of 0 equals 100. So that's that one. Let's go on to example number 2. See how I'm doing for time here. Not bad. We have dm dt equals 0.1 m plus 200. So in this particular problem, we need to divide everything by, well, basically this is all over 1, correct? So I'm going to go back to my red pen. Okay. This is all over 1. So we're going to divide both sides by 0.1 m plus 200 and multiply both sides by dt. When we do, basically these two things switch spots. All right, so we get dm over 0.1 m plus 200 equals dt over 1, which is just dt. Now, really important that those dm's, dt's, dx's, dy's always are in the numerator. You can't have division by those things and actually integrate. Okay, so now we'll integrate both sides. And when we integrate both sides, remember, when there is a constant in front of your variable that's being multiplied by it, after you integrate, you have to flip the constant and bring it out front, okay, out in front of your answer. So the answer to this side is the natural log of the absolute value of 0.1 m plus 200, but then you have to take that 0.1, which by the way is 1/10, and you flip it and bring it out front. So when you flip 1/10, you get 10 natural log of 0.1 m plus 200 equals, on the other side, you get t plus c. All right, so now what you want to do is get rid of that 10, right? You don't want the 10 in front of the natural log, so you divide everything by 10. And when you divide everything by 10, you get the natural log of 0.1 m plus 200 is equal to 1/10 t plus, call it another constant, d. All right, now once you have that, again, you raise e to the power of both sides to get rid of your natural log. E and natural log are inverse functions. So you get 0.1 m plus 200 is equal to e to the 1/10 t plus d, which is the same thing as, remember, e to the 1/10 t times e to the d, which is just another constant, right? So we'll call e to the d, we'll change it to a. So we'll say 0.1 m plus 200 is equal to a e to the 1/10 t. Once you have that, now you have to solve for m. So first thing I'm going to do is subtract 200 from both sides, so I'll get 0.1 m is equal to a e to the 1/10 t minus 200. And then to get rid of the 0.1, we multiply the whole equation by 10, right? Both sides by 10. 10 times 0.1 gives you 1 in front of your m, so you get m equals, now when you multiply a by 10, you got to change it to a new constant, so change it to b. So we'll say b e to the 1/10 t minus 2,000 when you multiply the 200 by 10. So now we plug in our initial condition. Now going up to our initial condition, m of 0 equals 1,000. This is the spot where we'll plug it in. So plug in m of 0 equals 1,000. So 1,000 for m, 0 for t. So 1,000 equals b e to the 0, right? Because 1/10 times 0 will give you 0, minus 2,000. So when you replace the e to the 0 with a 1 and you add 2,000 to the other side, you get 3,000 equals b. So the final answer to this differential equation, again, we take this piece, we take this piece, and once we've, oops, sorry, wrong piece. We take this piece, my goodness, where'd it go? There it is. And the 3,000 equals b. These two pieces, and we plug them, we combine them, replacing b, and we get m equals 3,000 e to the 1/10 t minus 2,000. And that one's done. So these are really quite simple. It's a very straightforward process. It is a process that you go through. So let's look at the next one. Another one that has a particular solution. We're 12 minutes in now. I know you have a short block today, but I think we should be able to get through all of the problems. So the next one is dy dt equals y squared times 1 plus t. So first thing we want to do is divide both sides by y squared and multiply both sides by dt. Okay, so I basically am doing this. Divide by y squared and then multiply by dt. When I do that, what happens is my y squareds disappear over here, my dt's disappear over here, and I end up with dy over y squared is equal to 1 plus t dt. Now integrating both sides is the next step, so let's go ahead and do that. Y to the negative 2, if I integrate that I get negative 1y to the negative 1, and that's going to be equal to t plus, using the power rule, we get 1/2 t squared, and then of course plus c. So negative 1y to the negative 1, I don't want to deal with a negative, so I'm going to go ahead and multiply through by that negative 1 right now, and then y to the negative 1 is 1 over y. So I'm going to say 1 over y is equal to negative t minus 1/2 t squared, and then I'm going to negate the c so that I'll just change it to a different constant, plus d. And then the next thing we'll want to do is basically take the reciprocal of both sides, but multiplying both sides by y and dividing both sides by this expression. Okay, so I'm flipping both sides, basically taking the left and the right, flipping them. So I get y equals 1 over negative t minus 1/2 t squared plus d. Well, not a big fan of the complex fraction, so I'm not really going to deal with that. I'm going to go ahead and multiply through by a 2 here. I could even multiply through by a negative 2 if I wanted, but you're going to have that negative no matter what, and right now it's in the bottom, okay? So I multiply the top and the bottom of this fraction by 2 to make my life easier, okay? So 2 on the top, 2 on the bottom, and I get y equals 2 over, distributing through the bottom, I get negative 2t, and I get rid of the 1/2 down there, so it's minus t squared, and then pick another one. So pick another constant, let's call it b. So now that's your solution. All we need to do at this point is plug in our initial condition. We know that y of 1 is equal to 2. So when y is 2, t is 1. So I'm going to go ahead and say 2 equals 2 over negative 2t minus 1, negative 2 times 1 minus 1 squared plus b. Solving for b very quickly, we get 2 equals 2 over negative 3 plus b. Cross multiply, we get negative 6 plus 2b is equal to 2, because this is over 1, of course, and then b ends up equaling 4. So you have b equal to 4, and you have this. Oops, I keep doing that. You have this is your solution. This is your constant. We take them, we put them together, and we get the final answer, which is the following. Y is equal to 2 over negative 2t minus t squared plus 4. Now, a lot of kids ask me the following question. Well, you don't really have to get rid of that fraction. You could still solve it without getting rid of the complex fraction that we got rid of way up here when we multiplied top and bottom by 2. Well, yes, you can, but it's not the proper way to express an answer. If you can get rid of fractions inside of fractions, you should do so. Now, you will not receive full credit on problems where you don't. All right, last one coming up. This is one where we're not given an initial condition. We are just given dr dt equals ar plus b. In case the bell rings before I finish, which I really doubt it will, your homework is page 539, 1 through 27 odd, 28, 29 through 41 odd. That is a lot of differential equations. They are easy, so it shouldn't be any issue for you to complete them. So let's move on. dr dt equals ar plus b. This one we have a lot of constants, which makes people very nervous. Now, this a and this b have to stick around in this problem. They are not arbitrary constants. They are constants that start in the problem, so you can't change them. Whatever happens to them remains in the problem. The arbitrary constant that you add on after you integrate is the only one that you're allowed to change. Okay? So, to do this problem, the first thing we want to do is get all of our r's on one side, all of our t's on the other. So I'm just going to divide both sides by ar plus b, multiply both sides by dt, and I end up with dr over ar plus b is equal to dt. And then when I do that, I'm going to integrate both sides. Now, when I integrate the right side, it's piece of cake. When I integrate the left side, I get the natural log of the absolute value of ar plus b is equal to t plus c. Whoops, what did I forget? Well, I have a constant in front of my r. Whenever I have a constant in front of my variable and I integrate, I have to flip that constant and put it out front. So I have 1 over a natural log ar plus b equals t plus c. I'm cooking soup. I have to turn it down. That's why I forgot my constant. Oh, there. Almost boiled the pot over. So I'm such a happy homemaker now. Here we go. Moving on to the next thing. Lost my train of thought. multiply both sides now through by a, because you always have to isolate your natural log before you raise e to the power of both sides. So I'll multiply both sides by a. I get natural log of ar plus b is equal to at plus, now this you can change, right? The c is an arbitrary constant, so you can change it to a d, right? When you multiply it through by something, you can change your arbitrary constant, only that one. Now, raising e to the power of both sides, we get this, and then we will cancel the e to the natural log. They are inverse functions, so we get ar plus b is equal to e to the at plus d. Oops. Plus d is part of the exponent, which is, of course, a times e to the at, right? Because whenever you have e to the at plus d, that's e to the at times e to the d, and e to the d is just another constant. So ar plus b is equal to a e to the at. Now, we still haven't solved for r. We've got to solve for r. Once we do that, we'll be done. First, subtract b from both sides, so we get ar is equal to a e to the at minus b. And then we need to divide everything by a, so when we divide everything by a, these cancel, and we get r equals, now when we divide the arbitrary constant capital A by a, we're just going to get another constant. So call it, I'm running out of constants, let's call it f times e to the at minus b over a. And that's our final answer for $1 million. And that's the end of my little lecture on separation of variables. So homework again, page 539, 1 through 27 odd, 28, 29 through 41 odd. That is due next class, which I believe is Thursday. And then on Thursday we will start applications, which are tons of fun. Have a great day, kids.